We have a problem, a math problem. And normally, math problems in astronomy are dull. They live in the margins. They argue over decimal places, confidence intervals, error bars that only specialists care about. They do not shake foundations. They do not make people uncomfortable. This one does. But because this math problem doesn't just tweak our understanding of 3I Atlas, it breaks it. It suggests that we don't actually know what we're looking at all. For months, we have been tracking this object, measuring its position, refining its orbit, calculating its speed, and most importantly, estimating its size. Those numbers felt solid, boring even. They fit our expectations. They fit our models. Then, on December 23rd, a new set of calculations dropped. And instead of refining the old picture, they destroyed it. The new numbers don't disagree politely. They don't fall within error bars. They don't argue about uncertainty. They flatly contradict everything we thought we knew. If you believe the measurements from May, this object is a giant. A 5-kilometer wide mountain of ice and dust, massive, heavy, immune to small forces. If you believe the measurements from this week, it's a dwarf, barely 1 kilometer across, a fragment, a lightweight shell. Those two realities cannot coexist. Physics does not allow an object to shrink by 80% and lose 99% of its mass in 6 months without catastrophically disintegrating. There was no explosion, no debris cloud, no fragmentation cascade, and yet 3I Atlas is still there, intact. So something is wrong. Either the telescopes are lying, or the math is broken, or we are dealing with an object that is actively defeating the assumptions built into our physics models. Today, we're going to open the hood on this paradox. We're going to walk carefully through what's now being called the size impossible calculation. And by the end, you'll understand why scientists are genuinely unsettled. Because when the numbers don't add up, that's usually where the discovery is hiding. Let's start with the new reality, the data that just dropped. On December 23rd, scientists tried to weigh 3I Atlas, not metaphorically, literally. Of course, you can't put a comet on a scale. You have to infer its mass indirectly. And for that, we use Newton's second law. Force equals mass times acceleration. We already know the object is accelerating, not just from gravity, but from something extra, the so-called rocket effect. As the object heats up, gas escapes from its surface, action and reaction. The gas goes one way, the object gets pushed the other. That push shows up as a non-gravitational acceleration. Tracking stations measured that acceleration precisely. The number is small, expressed in astronomical units per day squared. That sounds abstract, so let's translate it. It means that every single day, this object is being nudged to move about 13 kilometers per day faster than it would under gravity alone. 13 kilometers per day. That's tiny. About 1/5 millionth of Earth's gravity. A feather-light push, but applied continuously, day after day, it adds up. So now we have the acceleration term in Newton's equation. Next, we need the force. How hard is this rocket engine pushing? To answer that, scientists turned to the James Webb Space Telescope. Webb didn't guess. It measured the gas directly. 2 key numbers came out of those observations. First, how much gas is leaving the object? About 150 kilograms every second. Second, how fast that gas is moving, roughly 1,600 kilometers per hour. Once you have mass flow and exhaust velocity, you have force. And once you have force and acceleration, you can solve for mass. You ask the math a very simple question. How heavy must this object be for this amount of gas to give it this amount of push? The answer comes back unambiguously. 260 billion kilograms. If you assume the object is made of typical cometary material, porous ice, dusty aggregates, low density, that mass corresponds to a body about 1 kilometer across, maybe a bit less, 800 meters, 1 kilometer, somewhere in that range. On paper, it's clean, elegant, self-consistent. Case closed, right? Except no, because that 1 kilometer number is a nightmare. To understand why, we have to rewind the clock. Back to May, June, July, August, September. For 5 months, 3I Atlas was tracked obsessively. 230 observatories worldwide. Professionals, amateurs, robotic survey telescopes, precision instruments. They were measuring its position with absurd accuracy. About 0.028 arcseconds. Let me put that in perspective. That's like spotting a coin from 100 kilometers away. Sniper-level precision. And for 5 months, they weren't just tracking position. They were looking for the rocket effect. They were hunting for any sign of non-gravitational acceleration. Do you know what they found? Nothing. Zero. The object followed a purely gravitational orbit, no drift, no deviation, no detectable push. Now you might think maybe the acceleration was just too small to see back then. No, the detection limits were extremely tight. If the object had been experiencing anything like the acceleration measured later, they would have seen it. Instantly. The fact that they didn't see it places a hard upper limit on how much acceleration could have been present during that period. And this is where the trap snaps shut. Let's go back to Newton. If the acceleration is effectively zero, but the object is still releasing gas, then the mass must be enormous. Think of it this way. If I push a bicycle, it moves. If I push a cruise ship with the same force, it doesn't. The absence of motion implies a massive body. Harvard astrophysicist Avi Loeb crunched these numbers months ago. He asked, how massive would 3I Atlas have to be for the rocket push to remain undetectable given the observational precision? The answer is brutal. At least 33 trillion kilograms. That is 120 times heavier than the December calculation. And in terms of size, that mass corresponds to a body roughly 5 kilometers across, not 1. 5. So here's the contradiction, laid bare. The silence of the summer tells us we're dealing with a 5-kilometer giant. The motion of the winter tells us it's a 1-kilometer dwarf. Both conclusions are mathematically sound. They cannot both be true. So something is lying. How do you fix a 120-fold discrepancy? How do you bridge the gap between a mountain and a hill? Right now, scientists are scrambling to find a theory that can reconcile both timelines. And there are 4 serious possibilities. The first is the simplest, the diet. Could the object have lost the weight? Comets lose mass. That's what they do. But remember the numbers. To go from 33 trillion kilograms to 260 billion, it would need to lose 99% of its mass in a matter of months. That isn't melting. That's annihilation. If that much mass were lost that quickly, the object wouldn't still be a coherent body. It would be a diffuse cloud of debris. So mass loss can explain some of the discrepancy, but not all of it. Not even close. The second possibility is more subtle. The invisible push. This one is about perspective. We measure acceleration primarily along the object's orbital track, forward or backward. But what if the jets weren't pushing it that way? What if, during the summer, the outgassing was directed sideways or perpendicular to the orbital plane? In that case, the object could be accelerating without changing its speed along the orbit in a detectable way. It would be moving, but in a blind spot. Then, as it approached the sun, the object's orientation changed. The rotation axis shifted. The jets realigned. Suddenly, the same thrust became visible in our measurements. It's like a plane turning on its afterburners. You only notice the speed change if it's flying straight toward or away from you. The third possibility is the density trap. All of these calculations assume the object is made of normal cometary material. Fluffy, porous, low density. About 500 kilograms per cubic meter. But this is an interstellar object. We have no guarantee it's made of the same stuff as local comets. What if it's denser? Rocky? Metallic? Compact? A small, heavy object behaves very differently from a large, fluffy one. If the density assumption is wrong, the size estimate collapses. The fourth possibility is the most uncomfortable for scientists: the model glitch. There's a chance, small but real, that the initial zero acceleration measurement was simply wrong. Maybe the sensitivity was overstated, maybe noise masked the signal, maybe the early data were less clean than advertised. NASA has already revised the acceleration values downward multiple times since the first winter paper. Science is messy. Sometimes the data just aren't as good as we think, so where does that leave us? We have a ghost giant from the summer and a rocket dwarf from the winter. The truth is probably somewhere in the messy middle. But the existence of this paradox matters more than the resolution, because it highlights something fundamental. We like to think we understand these objects. We assign them numbers. We label them. We slot them into categories: comet, asteroid, size, mass, density. But 3i Atlas keeps reminding us of something uncomfortable. We are observing a stranger, an object born around a different star, under different gravity, with different chemistry and a different history. We are trying to force an alien puzzle piece into a solar system-shaped hole, and sometimes the edges don't fit. Right now, the models are being rewritten. New data is coming in every night, and with every update, the object seems to change. Is it big? Is it small? Is it heavy? Is it light? The fact that we still have to ask these questions months into the encounter is not a failure. It's the signal. Because the most exciting phrase in science is not eureka, it's "that's funny. That number shouldn't be there." Keep watching the numbers. Keep watching the gap. Because whatever resolves this paradox is going to tell us far more about interstellar space than any single image ever could.